Surface chemistry, chemistry that occurs at the interface of a gas with a solid, liquid and solid, or gas and liquid, is involved in the vast majority of bulk chemical synthesis used in industry. Most of the processes rely on heterogeneous catalysis to enhance their economic viability. There are three broad classes of surface reaction mechanisms. The Ely-Radiel mechanism describes a direct reaction between an atom or molecule that is adsorbed on a surface and a gas phase species, most likely an ion or radical. This type of reaction can be encountered in plasma surface chemistry and in semiconductor processing. A variation on this is the hot precursor mechanism, in which the gas phase species encounters the surface but does not fully equilibrate with the surface before it reacts with an adsorbate. But by far the most common surface reaction mechanism is in heterogeneous catalysis is the Langmuir-Henchelwood mechanism. This mechanism relies on the diffusion of molecules that are both adsorbed on the surface. At least one of the absorbed species must be mobile to create the collision that leads to reaction. In general, the kinetics of Langmuir-Henchelwood reactions are complex and depend on the coverages of the reactants in some form. Langmuir-Henchelwood kinetics is expected to depend strongly on the surface temperature and the availability of adsorption sites, particularly if the reaction occurs predominantly on special active sites. An example of the Langmuir-Henchelwood mechanism is CO oxidation. Recall that a mechanism must always sum to produce the stoichiometric overall reaction, hence the need for the stoichiometric number 1/2 in the first two steps. Adsorption of reactants and desorption of products are common to all Langmuir-Henchelwood reactions. So let's look more closely at the kinetics of adsorption and desorption. Desorption is always an activated process, and we expect it to exhibit Arrhenius behavior. Thus, we expect the desorption rate to follow a rate law of the form given here, where K is the rate constant and N is the order. But what are the concentration units? In surface reactions, we need to keep track of both full and empty sites, and we do so in terms of coverage. Coverage is defined as either the absolute coverage, sigma, which is the number of sites or adsorbates per unit area, or fractional coverage, theta, which is the number of sites or adsorbates divided by sigma naught. Note that sigma naught is either the total number of sites or the total number of surface atoms per unit area. Both definitions are used, so pay attention to the context of how sigma naught is defined. The fractional coverage is often referred to in units of monolayers, or mLs. A monolayer is a layer that is one adsorbate thick, and for most small molecules, that takes about 10 to the 19th molecules per square meter to form a monolayer. The kinetic order for desorption depends on the dynamics and molecularity of desorption. For evaporation, you generally get 0th order kinetics. For simple atomic or molecular desorption, 1st order kinetics are expected. But for a bimolecular process, such as the collision of two hydrogen atoms recombining and desorbing as an H2 molecule, 2nd order desorption is expected. Now let's consider the adsorption rate and what is known as the Langmuir model of direct adsorption. The rate of adsorption is limited by the impingement rate of molecules on the surface. The impingement rate is given by the Hertz-Knudsen equation. Remember to input molecular mass, that's lowercase m, in kilograms, or use molar mass, uppercase m, in terms of kilograms per mole. In addition, the pressure should be in Pascal and temperature, of course, in Kelvin. But not all molecules that strike the surface stick to the surface. The fraction that sticks is known as the sticking coefficient. The sticking coefficient often changes as the surface fills up with adsorbates. So we differentiate the initial sticking coefficient S0 from the sticking coefficient at arbitrary coverage S. Another thing to remember is that while desorption is always activated, adsorption can be either activated or non-activated. To calculate the rate of adsorption, we use a variation on an ideal model that was developed by Irving Langmuir, who was awarded the Nobel Prize in Chemistry in 1932. The fundamental assumptions of this model for molecular absorption are the following. The surface is homogeneous, particles are non-interacting, molecules only stick if they hit an empty site, and they reflect if they hit a filled site. The consequences of the model are that there's only one site and it has an absolute coverage sigma naught. Adsorption at one site does not affect another site. The fraction of impinging flux that sticks is proportional to the coverage of unoccupied sites. Adsorption is random, so there are no ordered structures or islands formed. Adsorption stops at one monolayer, and that's defined in this case in terms of the number of adsorption sites. The next step is to define the behavior of the sticking coefficient S as a function of coverage, the fractional coverage, theta. Let's assume a non-activated absorption, and so everything sticks if it hits an empty site and nothing sticks if it hits a filled site. Therefore, the sticking coefficient is equal to the probability of striking an empty site, and that's given by 1 minus theta. The sticking coefficient decreases because of simple site blocking. The rate of absorption is therefore the impingement rate times the sticking coefficient. We can extend the Langmuir model by defining the saturation coverage to be some number theta max rather than strictly 1. We can allow the initial sticking coefficient S0 to take on a value of something other than 1 when you hit an empty site. And you can introduce Arrhenius behavior to allow for activated adsorption. The generalized rate, therefore, becomes the rate of absorption is equal to the impingement rate times the initial sticking coefficient on an empty site. We have to account for the coverage dependence and then allow for the possibility of activated adsorption, which will introduce a temperature dependence to the rate as an addition from that activation barrier. The same ideas can be applied to dissociative absorption. If dissociation requires 2 adjacent empty sites, then the sticking probability varies with coverage, as does the probability of finding 2 adjacent empty sites. The probability of finding 2 adjacent empty sites is 1 minus theta, the quantity squared. Therefore, the sticking coefficient in dissociative absorption is equal to an initial sticking coefficient on an empty site, the coverage dependence, 1 minus theta squared, and again, we can allow for an activation barrier with that Arrhenius term. In either case, the sticking coefficient drops monotonically with coverage, either linearly for molecular adsorption or as 1 minus theta squared for dissociative adsorption. The coverage, the absolute coverage, as a function of time, is given by integrating the rate law, accounting for the coverage dependence of the sticking coefficient. The coverage is only linearly proportional to the exposure. Exposure is impingement rate times time. And the coverage is only linearly proportional to the exposure if the sticking coefficient is constant as a function of time. This is not in general the case. However, there are some very important exceptions including, at very low coverage, for metal-on-metal adsorption, and condensation onto multilayer films, such as the condensation of a vapor onto the surface of the corresponding liquid.